Assalamualaikum. In today's lesson, we take a revisit of a past upload on moment of force. But this time, we focus on non-parallel coplanar forces acting on a rigid body, specifically a mountain climber rappelling down a cliff face using a rope. How do we apply the torque principle in such a situation? Join me till the end of this video. Watch and learn. The question is, suppose that an 82.0 kilogram climber who is 1.90 meter tall and has a center of gravity 1.10 meters from his feet rappels down a vertical cliff with his body raised 35.0 degrees above the horizontal. He holds the rope 1.40 meters from his feet and it makes a 25.0 degrees angle with the cliff face. Question letter A. What tension force does this rope need to support? Question letter B. Find the horizontal and vertical components of the force that the cliff face exerts on the climber's feet. And question letter C. What minimum coefficient of static friction is needed to prevent the climber's feet from slipping on the cliff face if he has 1 foot at a time against the cliff? Shown in the diagram, we identify three major coplanar but non-parallel forces acting on the climber. We have the climber's weight W or mg equal to 804 newtons. As the climber holds the rope attached to the cliff face, an unknown tension force capital T in the rope also acts on him, directed at an angle 25.0 degrees with the vertical cliff face. To lower himself down the face of the cliff, all right, this is called rappelling. The climber does this with his body nearly horizontal and his feet pushing against the cliff. So, an unknown reaction force, F, is also exerted by the cliff on the climber's feet. Take note, the climber's body makes an angle 35.0 degrees from the horizontal. For clarity, we have a separate diagram to emphasize additional quantities that we need in our computations. The climber is holding the rope 1.40 meters from his feet. We label this distance as D1. All right? Now take note that this distance from the feet of the climber, all right, uh, to the point where he holds the rope, D1 is actually not perpendicular to the line of action of the force tension T. All right? So, We therefore specify here a line r sub 1 from uh, the fit, all right, to the line of action of the tension force T. All right. So um, the distance D1 and the perpendicular line R1 actually form an angle which we label here as angle phi, right? Hence, we can imagine a right triangle with R1 as the adjacent side, D1 as the hypotenuse, and the small length of the rope as the opposite side. And a little geometry will show that this angle phi is in fact equal to 35.0 degrees minus 25.0 degrees, or that is angle phi is 10.0 degrees. So the perpendicular line r sub 1, okay, can be expressed as uh, the value of d1, which is 1.40 meters, multiplied by the cosine of the angle 35.0 degrees minus 25.0 degrees, or that is cosine of the angle 10.0 degrees. All right. So the perpendicular distance r1, all right, is equal to 1.38 meters. For us to be able to compute the tension force capital T, which is our first target variable, we need to express its x and y components first. So for the x component, capital Tx, we have the equation Tx equals capital T multiplied by sine of the angle 25.0 degrees, right? And for the y component of the tension force T, the equation is T sub y equals capital T times the cosine of 25.0 degrees, right? So we shall come back to this uh, computation for Tx as well as Ty as soon as we have the value for the tension T, right? But for now, uh, using the torque principle, okay, we will let uh, point A, which is the contact point of the force F exerted by the cliff on the climber's feet, all right? We will let that point A be the axis of rotation. Choosing point A as the axis of rotation actually will make the torque due to the force F to be equal to 0. All right? This is because the force F, all right, uh, passes through point A, all right, or the axis of rotation that we will assume. So it will have no what we call lever or moment arm. But for the other forces, such as the weight W and the tension capital T, will have their corresponding torques, right? And starting with the torque due to the weight of the climber, W, okay, uh, we determine the torque produced by the weight, all right, denoted by uh, the Greek letter tau and subscript W, as in torque due to the force W, right? It is just equal to the magnitude of the weight and R sub 2, all right? R sub 2 is the perpendicular distance from the chosen axis of rotation, or point A, to the line of action of the weight W. All right. And the tendency for the torque produced by the force W is to make the body, that is the climber, to rotate clockwise, all right, about the axis of rotation that we have chosen, that is point A. So we emphasize that here, right? Uh, CW sub tau means um, this is referring to the torque that that is produced by the weight W, all right, which tends to make the body or the climber rotate in a clockwise manner about point A. That is the meaning of this notation, all right? And based on the formula for torque due to the weight W, all right, we just multiply the weight, which is equal to 804 newtons, and the value of R2, all right? The value of R2, or the lever arm R2, is just equal to 1.10 meters. 1.10 meters is given the problem as um, the distance from the center of gravity of the climber, all right, to his feet, which we have chosen as the axis of rotation, all right? And in relation to R sub 2, we can say that R sub 2, which is the adjacent side of the angle 35.0 degrees, while the distance 1.10 meters happens to be the hypotenuse, all right, of the imaginary right triangle. That's why we use cosine of the angle 35.0 degrees. In other words, the product of 1.10 meters and cosine of 35.0 degrees, right, is the perpendicular distance r sub 2. So with the help of your calculator, we can express the torque produced by the weight W about the chosen axis of rotation point A equal to 724 meter Newton. All right. We choose meter Newton as our unit for torque to distinguish it from the unit of work, which is Newton meter. The torque about the same axis, point A, that balances the clockwise rotation is provided by the tension T. Tension T has the tendency to cause the body to rotate in a counterclockwise direction. It is equal to the tension force capital T multiplied by the moment arm R sub 1. Right? Or we have the torque produced by the tension force T equal to capital T multiplied by 1.40 meters and multiplied also by cosine of the angle 10 degrees, which when simplified, we get 1.38 meters times the tension force capital T. And equating the two torques for the clockwise and the counterclockwise rotations, right, about the axis of rotation point A, we get 724 meter Newton equals 1.38 meter times the tension T. So solving for the tension T, we just divide 724 meter Newton by 1.38 meters, and we get the value of the tension force capital T equal to 525 newtons in three significant figures. Finishing our computations for Tx and Ty, all right? For Tx, we have 525 newtons multiplied by the value of sine 25.0 degrees, right? So with the help of your calculator, we get Tx equals 222 newtons. And for the y component of the tension T, that is Ty, okay, 525 newtons is multiplied by the cosine value of 25.0 degrees, which is 476 newtons. And moving on to part B, right? So part B requires us to determine the y and the x component of the force F, right? This time, we make use of Newton's law of equilibrium, right? There are three forces along the vertical. We have the y component of the force F, the y component of the tension T, and the weight of the climber, right? And Newton's law of static equilibrium tells us that the summation of the vertical forces must be equal to zero, all right? So the two upward forces, Fy and Ty, when added vectorially, right, would just be equal to the magnitude of the downward force, which is the weight W. And since we want to calculate the y component of the force F, that is F sub y, all right, we just subtract the weight W minus the y component of the tension T. That is, Fy equals 804 newtons minus 476 newtons. So we get the value of Fy, all right, equal to 328 newtons, also in three significant figures. Likewise, for the x component of the force F, since there are only two forces along the horizontal, right? The x component of F and the x component of the tension T. But since they are in opposite directions, that means the magnitude of the force Fx is just equal to the magnitude of the force Tx. That is, Fx must be equal to 222 newtons, also in three significant figures. Finally, in part C, okay, we are to find the coefficient of static friction mu of S, which is just okay the amount of the force Fy divided by the force Fx. That is, mu of S equals 328 newtons divided by 222 newtons. So that we get the value of the coefficient of static friction equal to 1.48 with no unit because Newton cancels out. All right. So the value has been rounded to three significant figures. All right. In most cases, the coefficient of static friction and that of the coefficient of kinetic friction are usually less than 1, right? But here we get a value of the coefficient of friction greater than 1. What does this mean? All right, so a value of mu s above 1 merely implies that the force of static friction is greater than the normal force of the surface on the object. All right? Based on our usual definition of static friction, which is the amount of static friction Fs divided by the normal force Fn. So obviously, the value of Fs corresponds to the value of Fy, which is 328 newtons. The normal force, which corresponds to the value of Fx, equal to 222 newtons. That's why, dividing them, we get a value of mu s that is greater than 1. All right? Um, this value of the static friction, all right, probably is deliberately done, okay, to prevent possible slippage, right? So in such sports like rappelling, probably they make sure that the climber is wearing a shoes, all right, a shoes that can provide uh, enough amount of what we call adhesion, so that when the feet or the shoes the climber is in contact with the cliff face, right? The attraction between the surface of the cliff and the shoes of the climber, right, is such that it will have what we call much amount of friction. And in the case of static coefficient of static friction, as shown here, it is greater than 1. So that concludes our lesson on this topic. Till the next episode, mabuhay. Mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.